देखो थोड़ा बुलाओ. So I will be writing on the board, and those students who have joined online, for you it will be little difficult, and you have to really coordinate with one of the students who is in the class to uh, you know get the notes that I am writing on the board. Okay. So remember, last class we talked about two types of routing. One was the distance vector routing, the other one is the link state routing. Okay. So both of these routing protocols, the general philosophy of distance vector as well as link state, these are used in some of the actual protocols that are used for the internet, actual routing protocols. One such routing protocol is called the routing information protocol, RIP in short, RIP. Now this RIP has also gone through different versions, okay, RIP v1, v2 like that. So what I am going to do is I am going to give you the general philosophy of the RIP protocol. Remember that the finer details of RIP etc. we cannot and we do not need to really go through in detail. It is sufficient to know uh, only the important or the salient points. আছে খুলে দিন, এটা চকটা খুলে দিন, এটা হচ্ছে না, কেটে দিন, দু তিনটে বাইরে রেখে দিন এখানে. So we are going to first talk about something called the routing information in short it is called RIP. So let us try to understand the general philosophy of RIP. So let's take a topology like this. And I told you already that when you talk about routing, we are talking about a collection of routers through which the packets are going to flow through. So we can basically, please do not talk. So basically, any network for that matter, and particularly if you are talking about the internet, we can represent the internet or any part of the internet using a graph abstraction. Okay. So RIP, the general philosophy of RIP is that it is based on something called hop count. Now we need to really understand what is a hop and what is this hop count. We will understand that. So this routing information protocol, it is a class of distance vector routing protocol. So two classes of routing protocols we talked about. One is distance vector, the other one is link state. So RIP belongs to this distance vector category. Okay. So hop count, we need to really understand that what is this hop count metric. So let us consider a topology like this, which is basically the graph based abstraction of part of a network. And let us assume that we have in this topology we have different routers R1, R2, R3, R4, R5, R6, R7 and R8. These are the different routers. Now, if a packet comes in, so from this router, using its routing table, when the packet goes to the next router, this is called one hop. The same thing from R2 to R3, this will be another hop. So now if we count, very simple metric, now if we count the number of hops between R1 and R3, it is going to be what? 1 plus 1 equal to 2. So 2 hops. So from R1 to R4, through this particular path, how many hops are there? 1, 2 and 3. 3 hops. Now if we call this path to be P1, another path between R1 and R4, this one if we call it as P2, and another path, this one if we call it P3. Now P1 has how many hops? P1 has 3 hops. P2 has how many hops? 2 hops. And P3 has how many hops? 1, 2, 3 and 4. 1, 2, 3 and 4. P3 has 4 hops. So now if we have to choose the path with the least hop counts, least number of hop count. So which path has the least number of hops or the lowest hop count? P2, right? So essentially what it is saying is that between a pair of source and destination nodes, you use the hop count to understand the distance between the nodes. Now this distance between the nodes, you can use not only hop count as a metric, but also there are different other metrics. For example, let us say the delay in propagating a unit packet from one point to another. Like this, actually there could be different other metrics also that are possible, but in routing information protocol only this hop count is used as the metric to understand the distance between two nodes. So one point very important that you need to understand is routing information protocol uses hop count as a metric. Second important information is that it follows the philosophy of distance vector routing. Clear? Now the third thing is basically based on this concept. Routing information protocol gives a specification that the maximum number of hop count that is possible is 15. That's a specification, right? It has got nothing to do with why 15, etc. So based on certain, it's a matter of design that the hop count is 15. So hop count of 15 means how many routers can it accommodate at the most? How many routers? 16 routers. Maximum 16 routers it can accommodate. Now I already told you that out of the 3 options that we had, P1, P2 and P3, in this case P2 has the lowest hop count. Now what happens if we have a scenario where both the paths have the same hop count? Let us say that only 2 options are there, 2 paths, and the least measure is such that there are 2 paths with the same count. Then how do you handle it? So RIP says that if same hop count, so when I say hop count, I mean the lowest number, right? The least number. So in that case, the packet should be sent, through both the paths. निधि फिर से बुलाओ, डस्टर चाहिए। अच्छा, so this is one of the, not one, these are some of the features of this RIP. Okay, now we are talking about what? We are talking about routing table, and last class we spoke about the routing table. Please refer to the notes. So let us talk about the routing table, because ultimately in any distance vector routing protocol, these routing tables in the routers, these will need to be updated. Okay, and last class we have seen that in general how the routing tables are updated in any distance vector routing protocol. Everybody has written down this part, and somebody can volunteer to send the picture to the friends who are joining through online. One of you can take the picture. So let me just write it. Could you please quickly take the picture? So you share with the friends who have joined online. Okay, so now we are going to discuss about how the RIP protocol updates routing table. So basically here it is going to follow the same distance vector routing protocol for periodic routing updates, but it comes with some speciality. So what are these specialties? So it uses the concept of something called the timers. Now there are different types of timers that are used in RIP. The first one is called the update timer or periodic timer. The second one is called the invalid timer or expiration timer, and the third one is called the garbage collection, no talking please, or flash timer. So this timer, basically this update or periodic timer, the maximum value for timeout is 30 seconds. This one is 180 seconds, and this one is 240 seconds. So what is this periodic timer? This periodic timer, basically this is the timer which keeps track of how often the router updates its routing table, and in turn basically how often it is sharing with the neighbors, right? What is it sharing? It is sharing the distance vector, and we spoke about distance vector, how it shares distance vector in general distance vector routing protocol. We have already seen that. So this periodic timer basically keeps track of this. This invalid or the expiration timer, what it does is that just in case the router gets disconnected from the rest of the network, any router gets disconnected from the rest of the network, then how long it is going to wait, the neighbor, how long it is going to wait to hear the routing update from its neighbor who has got disconnected. Okay, so during time the neighbor waits to hear update. This is the second one. And flash timer is that how long it is going to wait before, if a particular route becomes stale, right? It becomes stale because the another router is not reachable or something of that sort, that then how long it is going to keep it in the routing table before flushing it out or removing it as a garbage from the table. Okay, so time the neighbor router takes to remove a route. Route means stale route. Okay, stale route from its routing table. So these are some of the important features of this routing information protocol. Remember that routing information protocol, the actual specification of the routing information protocol is quite long, elaborate, lot of things are there, but not everything you need to know and you cannot remember in this short duration of time. So people who get certifications on routers, there are people who get, technicians who get certifications on routers. They need to know these routers inside out. Okay, so they know many things beyond what I just told you. So for example, you know that the company Cisco is quite popular for making routers. So there is something called Cisco certification. So people who get Cisco certification, they are like experts in dealing with routers. Okay, so they will know RIP protocol in really in depth. So for you, this is sufficient, and certain points I have mentioned in the slide. This is also something that you should go through in addition to going through the corresponding portion from your book. So I am not going to go through each of these because most of it will be a repetition. So please go through the algorithm. Okay, more or less based on what I just told you, but the exact nitty-gritties are given over here in this algorithm. So you go through this algorithm, how the old routes are removed, how the routing updates are done, etc. These are all captured through this algorithm. So I'm skipping this, and you need to really, it doesn't, so exactly how the routing tables are getting updated. This is also given over here. Now RIP basically has two types of messages. It handles two types of messages. One is called the request message, the other one is called the response message. What is the request message? It is the request that is sent by a router that has just come up, or by a router that has some timeout entries. Okay, so whenever a router gets introduced into the network, it starts its operations, etc. Then the request message is sent by that router. So this request message can ask about specific entries or all the entries basically, right? And corresponding to a request message, basically you are going to get, the router is going to get a response message, which can be either solicited or unsolicited. Unsolicited means sometimes actually the other neighbors, they are going to feed in different messages basically to the router. So that's going to be unsolicited. So a solicited response message is sent only in answer to a request message. It contains information about the destination specified in the corresponding request message. On the other hand, an unsolicited response message is sent periodically every 30 seconds or whenever there is a change in the routing table. So this is basically how, this is basically the format of these messages. Okay. The timers I have already told you, and another thing, just for the sake of your understanding, you can also go through these things like what are the different performance parameters for the routing information protocol. Okay. So with respect to how often the update messages are sent, with respect to how often the convergence happens in the forwarding tables. And this is something that I was telling you, that maximum 15 hops are supported in a particular domain, and a few other parameters like robustness. Okay. So these are the salient features of this routing information protocol. Any question? So now I'm going to talk about another protocol which is called the OSPF, Open Shortest Path First Protocol. Everybody is, did you take a picture of this one? Please take the picture. So if you have any question, please ask her. Now, let us try to understand the second protocol, which is called Open Shortest Path First, OSPF. Okay. So Open Shortest Path Protocol, on the in contrast to the routing information protocol, which is based on distance vector philosophy, Open Shortest Path First Protocol is based on the philosophy of link state routing. It is based on link state routing. So we'll come to this and understand how this link state routing happens in Open Shortest Path First Protocol. But few other features of this Open Shortest Path First Protocol is this term open. So basically what it says is that because it is open, it's an open standard, right? So it's standard, and it's a standard routing protocol, which is basically basically followed in many of the routers. Okay. So any kind of open standard, basically, as you know, right? So these are more attractive. So that is one of the reasons why OSPF is also very attractive. So many of the routers, basically, which are used in the internet, they follow the OSPF protocol. Now, which vendor is following which routing protocol? That is basically, vendor specific, right? So some vendor may use RIP, another vendor may use OSPF. So that basically depends on the particular vendor and its product. Now another thing is that this OSPF protocol uses something called the auto path decision. That means that on the fly basically the routes are going to get updated. So that is why it is also called the dynamic routing protocol. Now this OSPF, it came into picture to address the limitations of RIP. Remember what I told you? I said that RIP is designed in such a way that the maximum number of hops that will be supported is how much? 15, right? So maximum 15 hops, but here basically OSPF goes beyond. So in other words, you can think of it this way, that RIP is designed for smaller networks or the domain where the domain is small. So wherever you have the routing domain which is small, RIP protocol is useful. Whereas if you are going for a bigger network, bigger scale routing scenario, then OSPF would be better. So you remember that last class we spoke about this link state routing. In link state routing, I told you that the routers, they store the link state table. Right? These link state tables are stored in the routers. Now, here in OSPF, what happens is every router, it sends a hello packet, sends a hello packet to whom? Whom does it send? What does link state routing state? What is the fundamental difference between distance vector and link state? So there also the distance vector table was shared with the neighbors. Here also it is shared, but there is a difference. What is the difference? Do you remember what I told you? Who remembers? So in the case of distance vector routing, what happens? Only the distance vector is shared with the immediate neighbors, right? Whereas in link state routing, what is happening? It is shared, it is flooded all across in the network, isn't it? So look at your notes, previous notes, what I told you last class. So this hello packet or the pinging of the neighbors over here is done every 10 seconds. Now every 10 seconds basically it pings, it sends the hello packets. Now how long it is going to do? So let us say that in some case it doesn't get a response. It sends a hello packet, it doesn't get a response. So how long it is going to try? OSPF says that it is going to try for 40 seconds. So that means 40 seconds means how many times? 4 into 10 seconds, which is 4 tries. Clear or not? So basically what OSPF says is that it will try for tries 4 times. And if R2 is still not accessible, if R2 is still not accessible, so accessible means what? That it is not responding, no response. Then what happens? It says that R2 is going to, so if R2 is still not accessible, so R1 will remove the routing information to R2. Remove from where? Remove from its routing table. Now, in contrast, as I was telling you, the beauty of OSPF protocol is no max count on the number of hops. So basically, theoretically, unlimited number of hops can be supported. Another feature of OSPF protocol, so please take a picture. Done. So I'm erasing this part. Another feature of this OSPF protocol is called area wise communication. What does it mean? So basically what OSPF does is that around every router, this entire network is going to be divided into different areas. So this router would be belonging to area 0, and let us say that this is classified as the main router, and then you could have these as area 1, etc. Now every area 1 basically has a network of different routers like this. So essentially this looks like a clustering kind of approach, where the different routers basically, these are clustered into different areas. So this is another feature of OSPF. Now, as I was telling you that, like in the case of RIP, OSPF also, the detailed specifications of OSPFs is also very vast. Hundreds of pages of documentation are there, which is not feasible for a course like this. So it is sufficient to remember only some of the salient features like this, And the most important thing to remember is the main philosophy behind these routing protocols, which is link state or distance vector, and the detailed description of the detailed working of these routing protocol, these different, the two different philosophies of routing protocol. So you should work out yourselves, like what I did in the last class. You should work out how distance vector routing exactly works and how link state routing also works. So I'm not going to go through all of these. These are texts, right? So you please go through and try to understand. Okay. These are some of the terminologies that are used in OSPF. Okay. So router ID, then router priority, designated router, and backup designated router. Okay. So this designated router, for example, it is elected to minimize the number of adjacencies that are formed. Okay. So this DR basically distributes the link state. A stands for what? Link state. So basically this metric basically, right? So I am forgetting this thing. So to all the other routers, and the DR is selected in a broadcast network to which all the routers share their DBD. So like this actually, this thing, this backup. So these things basically you go through. I'm not going through each of them, but these are like simple things to understand. The main concept I have told you. Link state advertisement. LSA is link state advertisement. Okay. Now, in OSPF, there are different types of links that are used. So, there is something called the router link. Okay. This router link basically, it advertises the existence of a router as a node in the network. So that I exist, right? So I am a router. This router, through the router link, I will advertise that I am there. Now, this router link can be again classified to be of three types: transient link, point-to-point link, and stub link. So this transient link is used for announcing a link to the transient network. And what is this transient network? This is the transient network. So this transient network is connected to the rest of the networks by one or more routers. You see that this is the transient link which connects to different networks through to other routers. Then you have the stub link. This is the stub link which advertises a link to a stub network. So stub network means what? That this is a stub for an actual network, right, which is kind of abstracted from it. So this is called the stub link. And then you have the point-to-point link. This is basically between two direct routers. Link between two routers, exactly two different routers. It's going to be point-to-point link. Okay, so please go through all of these. And these are some of these different details. So in the book it is there. And so OSPF messages, basically 5 types of messages are used in OSPF. Type 1, type 2, type 3, type 4, and type 5. Type 1 is a hello message, like the one that I was telling you earlier. So this is a hello message. So these hello messages are used by the router to introduce itself to the neighbors. So whenever a router comes up, when you turn it on, these hello messages the router is going to share with the other devices in the network to say that it is existing. So this is type 1. Type 2 is database description message, which is normally sent in response to the hello message to allow a newly joined router to acquire the link state database. LSDB is link state database. So that means the link state table, basically the link state table. Then you have the type 3, which is the link state request message, which is sent by the router that needs information about a specific link state. Okay, this is type 3. And type 4, which is link state update message, which is used for building the link state database, this link state table basically, right? So this is used for that. And then you have the type 5, which is the acknowledgement message to create reliability in OSPF, like that. So like this basically all these. Now what is this algorithm that is used? So after each router has created the shortest path tree, the algorithm needs to use it to create the corresponding routing algorithm. The algorithm needs to be augmented to handle the sending and receiving of all the 5 types of messages that we just saw. Okay. So the exact algorithm is there in your book. No, so the details of the algorithms are not there. Okay, so just this much is sufficient. No, little bit. So this thing is only mentioned. Only this much is mentioned. Okay, so this is fine. Okay, and then like the RIP, basically, what are the performance measures of OSPF? So like update message here, update message, convergence of forwarding tables and robustness. So these different properties. You see that OSPF protocol is more robust than RIP. Okay, it is more robust. And here, so last time also we saw that generally in any link state routing protocol, which algorithm is used for computing the shortest path? The Dijkstra's algorithm. Okay, and remember, unlike in OSPF, sorry, unlike in RIP, where only the hop count was used as a metric to measure the distance, here basically in OSPF leaves it open. You can use any metric that, so it could be the physical distance between the routers also, right? Or any metric that you want to use, because ultimately what you are going to do is you are going to fall back on Dijkstra's algorithm, and Dijkstra's algorithm will model it as a graph and then compute the based on the metric basically the cost between the two different nodes, right? I'm assuming that all of you remember the Dijkstra's algorithm, Bellman force, all of these right? Very good. Okay, so that's the main thing. I don't believe that there is, yeah. So one last thing which I skipped before, let me just show you. It's not very important, but still, so that you are aware. Achha, everybody remembers the count to infinity problem? Last time I had explained by working it out, right? So we had a scenario like this, right? We had a scenario like this, that we have two routers A and B, and there is some node X which is trying to connect like this. Okay, so let us call it X, and these two routers as A and B. Then in between also you have another network. So we have seen like what is the problem that happens with the count to infinity problem. Okay, so that we have seen. If you have forgotten this count to infinity problem, this is a very important one. So please look at my notes from last time. Okay, I worked it out. So look at the recording, then you will be able to understand or recap what was there. The main problem with the main problem with distance vector routing protocol is that only the distance vector is shared between the neighbors, right? The main problem is only the distance vector is shared. That problem is not there with the link state routing protocol. The main problem is that only that column, the distance vector column, is shared with the neighbors. and with the immediate neighbors only. Now what happens when one of these nodes basically, one of these nodes get disconnected. So basically this link between X and A, you see that it has failed. So it becomes non-existent after some time. So this is where basically, when you try to update the routing table, you get into some problem which is called the count to infinity problem. Now there are some solutions basically which tries to overcome this particular problem. One of which is called the split horizon. So in split horizon, what it is suggesting is, so instead of flooding the table through each interface, each node sends only part of its table through each interface. So if according to its table, node B, so in this case node B, thinks that the optimum route to reach X is via A, then it does not need to advertise this piece of information to A. The information has already come from A, so A already knows. So B got the information about X from A only. So A, when it is advertising further, B doesn't need to again inform A about the presence of X. So node B, what it will do, it will eliminate the last line of its forwarding table, which contains this information, before it sends it to A. And node A basically keeps the value of infinity as the distance to X, because through direct observation, node X already knows that it is not reachable. Node A knows that X is not reachable. So it is going to keep that value of infinity. And later when node A sends its forwarding table to B, so when A sends the forwarding table to B, B also corrects its forwarding table. Okay. So the system will become stable after the first update, and both A and B will know that X is not reachable. So this is how, the problem was that, earlier in the count to infinity, everybody, they keep on updating that it becomes infinity to reach the other node through that other node, isn't it? So so earlier basically you see, to reach X, so from here also it is infinity, through B also it becomes infinity. So now you have tried to overcome this particular problem through split horizon. Now split horizon also has its own problem. So for this basically, this Poisson reverse can address to some extent. This Poisson reverse basically, it says that normally these routing protocols will use a timer. We have seen these timer based protocols. And if there is no news about a route after timeout, then the node will delete the route from its table. This is normal. Now when node B, in the previous scenario, that means the previous case that we have seen, eliminates the route to X from its advertisement to A, then node A cannot guess whether this is due to split horizon strategy or because B has not received any news about X recently. In that case, basically this Poisson reverse, it says that we can still advertise the value for X, but if the source of information is A, it can replace the distance with infinity as a warning that do not use this value. What I know about this route basically comes from you. Right? So these are two little, so this might be a little confusing. So what you do is work out that count to infinity problem yourself and then go through this once more. Then you would be able to, correlate with whatever these strategies they mention. Okay. So that's all. So nothing more in this part. So tomorrow we are going to meet at 8 o'clock. Only tomorrow. So tomorrow 8 to 10 will, as usual, we'll have class. And next week onwards, again we will go by the timing that Professor Aurobindo Gupta had circulated to all of you. Okay. So only for tomorrow 8 to 10. For only this section. Don't tell your friends in the other section they will have their timing as per what Professor Gupta has mentioned. But only for our class, because I have another meeting now, so I had to cut short of it today. So tomorrow we will have 8 to 10. Okay.